Something impossible is happening right now. And the strangest part is that you've lived your entire life surrounded by it without ever noticing. Picture yourself standing in the middle of the universe. Not metaphorically, not symbolically, but literally. Everywhere you look, in every direction, you are the absolute center of a cosmic sphere, bigger than anything the human mind evolved to understand. This isn't poetry, it's physics. No matter where you go, across continents, across the solar system, across the galaxy itself, the center follows you like a shadow. And yet the universe you stand in is supposedly infinite, a place with no edges, no walls, no boundaries, nothing to mark where existence ends and something else begins. How can you live inside infinity and still be trapped inside a cosmic bubble at the same time? That contradiction is the doorway into one of the deepest revelations in modern cosmology. The universe has an edge, but that edge isn't made of matter or energy or anything physical at all. The edge is made of time specifically, the amount of time light has had to reach you. And that means the edge you see is different from the edge someone else would see in another galaxy. Each observer is surrounded by a personal cosmic horizon, a perfectly spherical limit centered on them, defined only by the age of the universe and the speed of light. Imagine holding a flashlight in a pitch-black cave. The beam illuminates a circle around you, a boundary made not of objects but of visibility. Walk forward and the circle moves with you. Your illuminated zone never changes shape, but the scenery inside it constantly does. This is your observable universe. The difference is that your flashlight isn't made of photons. It's made of time itself. Now imagine this. Light has been traveling toward you since the universe began 13.8 billion years ago. That sounds like the farthest you could possibly see should be 13.8 billion light years away. But that simple logic collapses the moment you understand that space itself has been stretching during that entire time. The expansion of the universe has pulled galaxies farther away while their ancient light was still en route. By the time that light arrives, the galaxies that released it are not 13.8 billion light years away. They are more than 46 billion light years away. The universe didn't just grow, it inflated the very distance the light had to travel. And this inflation has a bizarre consequence. There are regions of the cosmos whose light will never reach you at all. Not tomorrow. Not in a billion years. Not in a trillion. Their photons are trying, racing toward you at the universal speed limit, but the very fabric of space is expanding faster than they can close the gap. That creates an invisible wall around your reality, a spherical frontier beyond which information is forever sealed. This is why you live inside a cosmic bubble, even though the universe itself doesn't have a physical boundary. But here's where things become even more mind-bending. This bubble does not mean you are special. It simply means the laws of physics draw a personal horizon around every observer in existence. An alien on a planet 2 billion light years away has their own bubble, their own cosmic sphere centered on them, containing galaxies you can never see. Meanwhile, you can see galaxies that this alien never will. The universe reveals a different version of itself to every location inside it, and yet no place is privileged. There is no universal center of expansion, no grand origin point that other galaxies are fleeing from. Every point in space behaves as if it is the center because expansion happens everywhere at once. And so you find yourself occupying the exact middle of the observable universe, not because the cosmos revolves around you, but because your vision does. You are inside a cosmic sphere because the universe is younger than infinite distance. You are the center because the laws of relativity make you the anchor point of your own perception. Infinity surrounds you, but only a tiny fraction of it has had time to reach your eyes. And so, before we go deeper, before we approach the stranger frontiers of cosmic edges, remember this. The horizon you see is not the boundary of the universe. It is simply the maximum distance over which reality has had enough time to introduce itself. Everything beyond that is still out there, endless, unreachable, invisible, and stranger than anything you can imagine. Imagine an ocean with no shore, no islands, no seafloor, just endless water stretching forever in every direction. Now imagine being told that although this ocean is infinite, you personally can only ever explore a tiny bubble of it, and the boundary of that bubble isn't made of water, but of time itself. This is the paradox at the heart of our universe: infinity with limits. The cosmos may extend endlessly, but we can only ever interact with a finite region carved out by the age of the universe and the stubborn maximum speed at which information can travel. This idea feels wrong at a gut level. We expect edges to be physical, a cliff, a wall, a boundary you can touch. But the edge of the observable universe is nothing like that. There is no membrane out there holding galaxies back. They're not piling up against a cosmic fence. Instead, the limitation exists because the universe hasn't existed long enough for light from those regions to reach us. That's the key. The boundary is defined not by space but by time. And understanding this is crucial because it reshapes everything you think you know about the universe. When we say the universe might be infinite, we mean that space could continue forever without looping, folding, or ending. There might be more galaxies than grains of sand on all the beaches of Earth, and beyond that, more galaxies, and beyond that, more still. You could travel in a straight line for all eternity and never hit an edge. But here's the twist. Even if the universe is infinite, your access to that infinity is brutally limited. The observable universe, the only region that has ever communicated with you, is a sphere about 92 billion light-years across. Everything beyond that lies outside your cosmic horizon, not because it's gone, not because it's unreachable in principle, but because the universe simply hasn't been around long enough for its light to get here. Infinity exists. The evidence just hasn't arrived yet. To grasp this, imagine turning on a lantern in a vast, infinite wilderness at night. The light radiates outward, illuminating more and more of the darkness over time. The longer the lantern burns, the larger the sphere of visible landscape becomes. But even after hours, days, or years, the illuminated area is still finite, still tiny compared to the infinite wilderness surrounding it. Your lantern has no hope of lighting the entire infinity. It reveals only the portion for which enough time has passed. The universe works the same way. Our cosmic lantern, the Big Bang, has been shining for 13.8 billion years. That's how long photons have been racing outward across space. But because the universe expands as those photons move, the illuminated region is bigger than 13.8 billion light-years. Much bigger. The expansion stretches the light's path, transforming a 13.8 billion-year journey into a 46 billion light-year distance. And this is why the observable universe has a boundary. Not because infinity ends, but because time has not yet allowed more of it to be revealed. This leads to a profound realization. What we call the universe in casual conversation is really just the part we can see. The actual universe could be thousands, millions, or an infinite number of times larger. Everything we've ever detected comes from within our bubble, and everything we've ever theorized about the universe beyond it comes from extrapolation. Maybe the rest of the universe looks just like what we see here. Maybe it's filled with galaxies, dark matter filaments, and vast cosmic voids. Maybe the same physical laws apply everywhere, or maybe not. Maybe the universe transitions into regions with different structures, different constants, even different physics. Maybe our observable bubble is just one patch in a cosmic quilt much more complex than anything we can imagine. But here's the unsettling truth. We will never know. Not because we lack technology, but because physics forbids us from receiving the information. The limit is permanent, absolute, time-stamped into the structure of reality. Even if you waited 1 trillion years, your observable sphere would grow, but only slowly, and only into regions whose ancient light is just now arriving. The galaxies currently beyond your horizon will remain hidden forever, because their light will never close the expanding distance. Infinity may be out there, but only a fraction, an ever-changing sliver, will ever be visible to any observer. And yet, despite this impossibility, despite this built-in limitation, the part we can see already contains 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars, each star potentially hosting worlds. And that is only the tiny slice we are permitted to glimpse. The universe's edge is not an edge at all, but a reminder that we exist inside a horizon defined by the speed of light in the age of everything. Infinity surrounds us, but we see only the part that time allows. If you want to understand why the universe has an edge you can never cross, you have to stop thinking about space as the thing that limits you and start thinking about time instead. Time is the architect of your cosmic prison. It draws the walls, sets the distance, and decides which parts of reality you're allowed to experience. And the rule it enforces is simple. Light, the fastest thing in existence, can only travel so far in a finite amount of time. Everything you will ever see or measure or detect depends on light having enough time to complete its journey. That means the boundary of your observable universe isn't a physical barrier, but a deadline, a hard cutoff, a limit imposed by the amount of time the universe has existed. If something is beyond the distance light could travel since the Big Bang, then no signal from it has ever reached you. And if no signal has ever reached you, then as far as your senses, your instruments, and your physics are concerned, it might as well not exist. Now consider this. Light moves at 299,792 kilometers per second. Nothing in the universe outruns it. Yet even at that unimaginable speed, it hasn't had enough time to cross the full expanse of the universe. The cosmos may be infinite, but light has only had 13.8 billion years to explore it. But here's where the universe plays its first big trick. If space were static, if distances never changed, then the most distant thing you could see today would sit 13.8 billion light years away. 1 year of travel equals 1 light year of distance. Simple. But the universe is not static. Space itself has been expanding since the very beginning. While light has been racing toward you, the space it travels through has been stretching like cosmic taffy. Imagine running on an escalator that moves backward faster than you can walk. You try to make progress, but the moving ground cancels it out. Now imagine the escalator gradually speeding up as you go. Even if you run faster, the escalator wins. That's what light is dealing with. The space it traverses expands underneath it. By the time photons arrive here, the galaxies that emitted them have been dragged much farther away. Light that took 13.8 billion years to travel actually comes from regions now more than 46 billion light years distant. That number will keep increasing as the universe ages. And this is the root of the paradox. Time defines the maximum journey light can make, but expansion stretches that journey into a much larger physical distance. The result is a horizon, a cosmic cutoff, beyond which the universe remains forever hidden, not because it doesn't exist, but because time has not permitted its reveal. But this edge is stranger still. Because expansion accelerates due to dark energy, space far from us expands faster than space near us. Galaxies beyond a certain distance are being carried away faster than light can travel toward us. Their photons try to approach but lose ground as the expanding space stretches the distance between us faster than light can close it. So while the observable universe grows slowly over time, as ancient light finally arrives, another boundary is shrinking. The event horizon, the limit beyond which no light emitted today will ever reach us. Everything beyond it is already lost to the future, even though we can still see its old light. Time acts like a double-edged blade. On one side, it allows more distant ancient light to arrive, expanding what you can see from the past. On the other, it pulls the future away, reducing what you can ever interact with. Time enlarges your past but erases your future, and all of this springs from the simplest law in nature. Nothing can travel faster than light. Because of this restriction, time creates a limit to visibility, and expansion transforms that limit into a horizon tens of billions of light years wide. The universe's edge is, in the purest sense, a time horizon. You're standing in a cosmic theater, and the curtain around you isn't made of fabric, it's made of time. You are watching only the part of infinity whose light has arrived. The rest is still performing behind the curtain, scenes that have been running for billions of years but whose light hasn't reached your seat. And here's the final twist. Even as you watch, the stage is changing. More of the ancient light makes it to you each second, revealing new territory from the deep past. Yet the expansion ensures that vast regions are receding so quickly that no future light from them will ever arrive. Time giveth and time taketh away. And whether the universe is infinite or merely unimaginably large, your access to it will always be carved out by the simple question, has its light had time to get here? Wherever you stand in the universe, you are the center of everything you can see. That sentence feels arrogant, almost cosmically egotistical, but it is not a statement about importance. It is a statement about geometry and the finite speed of light. If you floated in the void halfway between galaxies, you would still be the center. If you traveled 5 billion light years in any direction, the center would move with you. Any observer, anywhere, becomes the middle point of their own visible universe. And this isn't an illusion or a trick. It's the most natural consequence of living inside a cosmos where information travels at a fixed speed and where time has a beginning. Imagine you and a distant alien both turn on flashlights at the same moment. The expanding spheres of light around each of you grow outward equally, centered on your positions. That's exactly what the observable universe is. A sphere of information centered on your location, formed by 13.8 billion years of light racing toward you. Another alien, somewhere else, has their own sphere, overlapping with yours in some regions and diverging in others. Neither observer has a privileged position. Both are the geometric center of what their senses allow them to perceive. And this leads to one of the most profound truths in cosmology. Every observer believes the universe is expanding away from them, equally in all directions. If you watch the sky, distant galaxies are drifting outward, like dots on an inflating balloon. Turn around and the opposite galaxies also drift outward. Look left, they recede. Look right, same story. No matter where you look, expansion behaves symmetrically. It gives the strong impression that you are at the very center of everything. But so does every other galaxy. The reason is simple. Space doesn't expand from a central point. It expands everywhere at once. There is no center of the universe. There is no place you could travel to and say, here is where the Big Bang happened. The Big Bang didn't happen at a location. It happened everywhere. All of space participated. All of space has been expanding ever since. To understand this better, picture a giant sheet of rubber with coins glued to it. If the sheet stretches, all the coins appear to move away from one another. But no coin is special. No coin sits at the center. The movement is a consequence of the sheet expanding, not the coins drifting on top of it. Replace the sheet with three-dimensional space, and you have the universe. Because expansion happens everywhere, every observer sees all distant objects receding from them, making their position appear central. And because the speed of light is finite, every observer sees only the bubble of space from which light has had time to reach them. Combine these two facts, and you get a universe in which each observer becomes the center of their own cosmic sphere. This raises a powerful question. If everybody is the center of the observable universe, then what is the real universe like? What shape does it have without observers? The answer is both simple and dizzying. Without observers, the universe has no center at all. The center exists only relative to each viewpoint, like standing inside a sphere of stars that rearranges itself based on where you look from. The observable universe isn't the universe. It's the footprint of your cosmic perspective. Now imagine two galaxies separated by billions of light years. One sees the other as a tiny smear of ancient, red-shifted light, and the other sees its partner the same way. Their observable universes overlap, but each contains regions the other can never perceive. There are galaxies visible from one that the other will never detect. There are entire cosmic structures one can observe, and the other never will. Every location comes with its own access to infinity, a private slice of cosmic history sculpted by its position in space in the time available for light to arrive. This perspective-centered reality means that if you move through space, even by small amounts, you change your visible universe. New regions come into view. Others fall behind the horizon. If you teleported 1 million light years away instantly, your observable sphere would shift, revealing galaxies and structures invisible from Earth. But here's the incredible part. Even though your observable universe moves with you, its shape, its size, and its boundary remain the same. It expands as time moves forward, but remains perfectly centered on your position. It follows you like a cosmic aura, always centered, always spherical, always defined by the age of the universe. You are not the center of the universe, but you are the center of the universe you can see. And so is every being in every galaxy in the cosmos. This is not ego, it is geometry. It is not privilege, it is perspective. And it is a reminder that the universe we observe is not absolute reality, but a personal window carved out by time, distance, and the unbreakable speed limit of light. If you want to understand why distant galaxies seem to flee from us, like frightened birds scattering from a tree, you have to abandon the idea that they're actually moving through space and instead realize that space itself is doing the moving. This is one of the most counterintuitive truths in cosmology. Galaxies are not speeding away from us like rockets. They are mostly sitting still, anchored in their local patches of space like raisins embedded in rising dough. As the dough expands, the raisins grow farther apart, even though they hardly move on their own. That is the behavior of our universe. Space is the dough. Galaxies are the raisins. And the expansion of the dough isn't just a metaphor. It's a literal stretching of space-time, a geometric transformation happening everywhere at once. When you hear that galaxies recede from us at thousands or even millions of kilometers per second, it's natural to imagine them physically traveling through the cosmos. But that picture is wrong. They remain mostly stationary relative to the fabric around them, while the distance between them increases. This distinction matters because it explains why the universe has no center and no edges. If galaxies were flying outward from a central explosion point, we would expect to find a center somewhere. But there is none. Every observer sees the same expansion in every direction because space is expanding uniformly. Imagine ants standing on the surface of a balloon. As the balloon inflates, each ant sees all other ants moving away. None can point to the center of expansion because it lies not on the surface, but in a dimension the ants cannot access. In the same way, the expansion of our three-dimensional universe isn't happening into anything. There is no external space around ours. Space is expanding into itself. This raises an important question. If galaxies aren't moving, then how can some appear to be receding faster than the speed of light? Shouldn't that be impossible? Only if we cling to the idea of motion through space. But when space itself expands, no physical object is breaking the cosmic speed limit. The speed limit applies only to motion within spacetime, not to the stretching of spacetime itself. When we measure a galaxy receding at twice the speed of light, we are not seeing it violate relativity. We are seeing the distance between us and the galaxy increase faster than light can close that distance. The galaxy is still locally stationary. The space between us is doing all the work. And the farther a galaxy is, the faster that space stretches. This pattern recession velocity increasing linearly with distance is known as Hubble's law. It explains why galaxies half as far away recede at half the speed, and galaxies twice as far recede at double the speed. Expansion isn't pushing galaxies outward, it's scaling up the distance everywhere. Even nearby galaxies feel this stretching, but their gravitational bonds are strong enough to overpower it. That's why the Andromeda galaxy is actually moving toward us. Gravity outweighs expansion on small scales. But on cosmic scales, hundreds of millions or billions of light years, gravity fades into irrelevance and expansion dominates. Space stretches, distances grow, and galaxies drift apart not because they choose to move, but because the universe chooses to expand. Now picture a grid drawn on a rubber sheet. Each intersection of the grid represents a galaxy. As the sheet stretches, the grid expands. Distances grow, angles remain the same, and no point is special. If you stand on one of those intersections, you see all other intersections moving away. Look in the opposite direction and the same pattern emerges. You appear to be at the center of the stretching, even though no center exists. This is why expansion creates the illusion that we occupy a privileged position. The truth is far more elegant. Expansion looks identical from every viewpoint because it is not motion at all, but a transformation of the underlying stage on which motion happens. And here is where the illusion grows even more surprising. Because expansion accelerates over time, the stretching becomes stronger in the distant parts of the cosmos. There's more space out there to stretch. and the cumulative effect becomes overwhelming. Think of it like elastic material. Stretch a small segment slightly and it barely changes. Stretch a huge segment by the same percentage, and the total change becomes enormous. The universe works exactly the same way. Space near us expands slowly, but space billions of light years away expands much faster simply because there is so much more of it to stretch. And so galaxies we observe at the far edge of visibility aren't racing away through empty void. They are being carried by an expanding fabric whose behavior grows more dramatic with distance. Understanding this makes many cosmic mysteries clearer. Why do distant galaxies appear redder than expected? Because their light is stretched along with space. Why can light from galaxies receding faster than light still reach us? Because the expansion rate changes over time, sometimes allowing photons to gain ground. Why is the universe pulling itself apart faster with every passing moment? Because dark energy drives the expansion from the fabric itself. And all of these revelations become intuitive once you let go of the idea of galaxies flying through space and instead accept the truth. Space is expanding, and everything inside it simply rides the wave. You are not watching galaxies move, you are watching the universe grow. There is a rule in physics so fundamental that it sits at the foundation of everything from relativity to quantum field theory. Nothing can move faster than the speed of light through space. No matter how powerful your engine, no matter how advanced your technology, no matter how much energy you pour into your spacecraft, you will never outrun a photon. This limit feels absolute, unbreakable, woven into the fabric of reality itself. And yet when we look deep into the cosmos, we routinely observe galaxies receding from us at twice the speed of light, 10 times the speed of light, even more. How can this be possible? How can the universe itself break the very law it imposes on everything within it? The answer is both subtle and astonishing. The speed limit applies only to motion through space, not to the expansion of space itself. And this difference is the key to understanding how the universe hides entire regions behind a cosmic speed curtain. Imagine two ants standing on a giant rubber sheet. They cannot run faster than their own maximum speed. But if the sheet stretches, pulling them apart, they can recede from each other faster than either ant can run. Neither ant breaks its speed limit. The sheet simply grows underneath them. Now scale that up to cosmic proportions. Galaxies are the ants, and the fabric of space is the rubber sheet. Space stretches, and the galaxies ride the expansion. Their local movement remains slow, often just tens or hundreds of kilometers per second. But the stretching across billions of light years adds up. The more space between two galaxies, the more room there is for expansion to amplify their separation. At a certain distance, currently around 14.4 billion light-years, the recession speed equals the speed of light. Any galaxy farther than this distance is technically receding from us faster than light, not because it is zooming through space, but because the space between us expands too quickly. And once a galaxy crosses that threshold, a dramatic change occurs. Any new light it emits right now will never reach us. The photons try to move toward Earth, but cannot close the distance faster than expansion increases it. It's like trying to swim toward shore in a river whose current flows faster than you can swim. You move forward relative to the water, but backward relative to the land. At these enormous cosmic distances, photons behave the same way. They move forward through space but move backward relative to us because space expands faster than they can travel. But here is the twist. We can still see many galaxies that are receding faster than light. Their ancient light, emitted billions of years ago, began its journey when the expansion rate was slower. As the photons traveled inward, they crossed regions where expansion was less dominant. They gained ground and eventually reached us, even though the galaxies were always receding faster than light. This is one of the strangest facts in cosmology. You can observe galaxies that have always been and always will be superluminal in their recession. The photons we detect are survivors from a time when space was less hostile to their journey. But any new photons those galaxies emit today will never arrive. They are already lost to cosmic expansion. Their present is forever disconnected from our future. That creates a second boundary inside the observable universe, the event horizon. It currently lies around 16 billion light years away. This is not the edge of what we can see. It is the edge of what we can ever influence or receive new information from. Galaxies beyond the event horizon can still be visible because we are catching the light they emitted long before crossing that boundary. But their present and future states are sealed away. No message from us can reach them. No message from them can reach us. They exist inside our observable sphere, but outside our causal sphere. They are visible ghosts drifting on the wrong side of a cosmic one-way mirror. And this superluminal recession isn't rare. Most of the galaxies in the observable universe, billions upon billions of them, are already receding from us faster than light. We just happen to be receiving old photons. Last glimpses from a time when communication was still possible. Over billions of years, these galaxies will fade, stretch, redshift, and eventually disappear from our sky entirely, leaving behind only the gravitationally bound structures around us. The universe is obedient to its own laws. Nothing moves faster than light through space, but the fabric of space is under no such constraint. It stretches at any rate the cosmological equations demand. And because of that stretching, huge portions of the universe are forever slipping beyond reach, carried away on an expanding tide faster than the fastest traveler in the cosmos. The speed of light is not the speed of the universe. It is only the speed of what moves inside it. To understand the structure of the universe and your place inside it, you must accept that there isn't just one cosmic boundary. There are two, and they behave in completely opposite ways. The first is the particle horizon, the farthest distance from which light has had time to reach you since the universe began. This is the limit of what you can see, the boundary of everything that has ever managed to send a photon into your telescopes. It sits today roughly 46 billion light-years away in every direction, forming a sphere around you that defines the observable universe. Every image you have ever captured, every star you have ever studied, every galaxy you have ever mapped, all of it lies inside this immense bubble. But the particle horizon is not fixed. It grows as time passes. Each second, ancient light that has been traveling for billions of years finally arrives, revealing new, more distant regions of the universe. Your visible cosmos grows like an expanding spotlight in a dark room, slowly illuminating more of the infinite landscape around you. The second boundary is far more sinister. The event horizon, the maximum distance from which light emitted right now can ever reach you in the future. This is not the limit of what you see. It is the limit of what you can ever communicate with, influence, or receive new information from. Galaxies closer than the event horizon can still send signals to us if we wait long enough. But galaxies beyond it never can. Not now, not ever. And here is where the universe reveals one of its cruelest tricks. The particle horizon expands over time, but the event horizon shrinks. One shows you more of the past as time moves forward. The other erases your future access to the cosmos. These two boundaries carve your universe into three regions. First, the reachable universe, the tiny inner bubble of galaxies close enough that a signal we send today could one day reach them. This region is incredibly small compared to everything else. Only galaxies within roughly 16 billion light-years are part of this privileged zone. Everything beyond that distance is receding too fast for any signal to catch up. Second, the visible but unreachable universe, a massive contrast. These are galaxies you can still see, the ones whose ancient light continues arriving, but which are already too far away for future communication. Their photons from billions of years ago are still en route toward us, but any new light they emit now will never bridge the growing gap. When their last ancient photons arrive, they will fade away forever. Third, the permanently hidden universe, everything beyond the particle horizon, where no light has had enough time to reach you at all. This region could contain infinite galaxies, infinite stars, infinite structures, but no matter how long you wait, you will never see them. They exist beyond time's reach. These two horizons, the particle and the event, are not abstract mathematical curiosities. They define everything you can observe and everything you can influence. They tell you which galaxies are still sending you light, which galaxies are already lost, and which galaxies will never become visible even if the universe lasts forever. Stand back and look at the consequences, and the picture becomes even stranger. The particle horizon grows because ancient light is still catching up to us. But the event horizon shrinks because dark energy accelerates the expansion, cutting us off from more and more of the universe as time goes on. Imagine a cosmic documentary being filmed everywhere in the universe. The particle horizon is the footage from the past finally arriving in your inbox. The event horizon is the camera cutting out on the rest of the story. The longer the universe expands, the more of the documentary goes permanently missing. Entire galaxies, entire clusters, entire cosmic structures drift out of reach as the event horizon contracts inward, like a tide pulling the universe away from us. And here is the most unsettling detail. Eventually, in the far future, these two horizons approach each other. The amount of the universe we can see will grow slower and slower. The amount of the universe we can reach will shrink faster and faster. One day, billions of years from now, the observable universe will stop growing. It will freeze in size. Meanwhile, everything not gravitationally bound to our local group will fade into the darkness, leaving us with a sky that grows emptier with every passing era. You live at a rare moment in cosmic history, the brief window where the universe is both visible and rich with galaxies. One horizon expands, the other shrinks, and you are caught between them, watching as the cosmos reveals its past while erasing your future. When you look deep into the night sky, far beyond the stars of the Milky Way, past distant clusters and filaments of galaxies, you are not seeing the universe as it is, you are seeing the universe as it was. Light takes time to travel, and the farther you look, the older the light becomes. This seems simple enough, but hidden inside this fact is one of the strangest and most haunting consequences of cosmic expansion. Many of the galaxies we observe today no longer exist in the state we see them, and some may not exist at all anymore. They have already crossed the cosmic event horizon, drifting beyond the reach of all future light, even as their ancient photons continue to arrive. In other words, we are watching ghost galaxies images frozen in time, snapshots from billions of years ago that bear no connection to the galaxy's present reality. It's like watching a live stream that secretly ended eons ago, while the final frames from the past are still trickling in. Imagine pointing a telescope at a galaxy 12 billion light-years away. The light you detect left that galaxy when the universe was less than 2 billion years old. You are witnessing a cosmic relic, a baby galaxy in its early stages of formation. But here's the twist. While that ancient light has been traveling toward you, the galaxy itself has raced away through expanding space. Today, that same galaxy may be 30 or 40 billion light-years distant far beyond the cosmic event horizon. Any light it emits now will never reach Earth. Expansion outpaces the photon's ability to close the gap. But because the light emitted long ago started its journey during a slower era of expansion, it can still arrive today, giving us one last glimpse into a past that no longer exists. It is as if the universe has built-in time delays, revealing the cosmos in a slow drip of ancient scenes while the present races out of reach. And the effect grows stronger with distance. The farther away a galaxy is, the more extreme the time gap becomes. Look at a galaxy 1 billion light-years away, and you see it as it was 1 billion years ago. Look 10 billion light-years away, and you see the universe when it was young and turbulent. Look all the way to the edge of the observable universe, and you are seeing light that left just 380,000 years after the Big Bang, long before the first stars formed. But even these snapshots are just shadows now. The galaxies that emitted the oldest light we observe have already crossed so far beyond the event horizon that their modern states are inaccessible forever. Their final photons, the last bits of information they managed to send before expansion, carried them past the cosmic point of no return, are still on their way to us. One day those last photons will arrive, and after that, nothing more. The galaxy will fade into invisibility, its image stretched to longer and longer wavelengths until it becomes indistinguishable from the background glow of the universe. Eventually, it will vanish entirely, not because it ceased to exist, but because the universe stopped letting its light reach us. We will never know what happened next, whether it merged with another galaxy, collapsed into a quasar, gave birth to trillions of stars, or died in silence. That part of its story lies outside the realm of physics we can access. This means that a significant fraction of the galaxies visible today are actually messages from cosmic history, not active members of our contemporary universe. They are ghosts in the strictest scientific sense phenomena that persist only in the form of ancient light, and as time passes, more galaxies will join them. Every day, thousands of galaxies cross the cosmic event horizon, receding so fast that light emitted from them now will never reach us. Their old light continues to stream in, showing us their youth, their early stars, their ancient collisions, but their present reality has already slipped away. You might think of this like watching a distant fireworks display. Light from each explosion travels outward, and even if the fireworks stop, you still see flashes for a while as old light continues to reach you. But in the cosmic version, the fireworks are still ongoing. You just can't see the new ones because the universe is expanding too quickly. In the coming billions of years, the universe will become stranger still. The visible sky will grow emptier as more galaxies fade beyond the event horizon. Our view of the cosmos will shrink not because the universe stops expanding, but because the information from beyond can no longer reach us. The universe's past will remain beautifully illuminated, but its future will grow darker and more distant. What we see today is a collection of frozen postcards from a cosmos that has already changed beyond recognition. We are surrounded not by the universe as it is, but the universe as it once was, a vast gallery of cosmic ghosts whispering stories from billions of years ago. Before stars existed, before galaxies assembled, before the universe became transparent, there was an era so alien and violent that no human analogy can truly capture it. For the first 380,000 years after the Big Bang, the universe was not a place where light could travel freely. It was a cosmic fog, a seething, blinding plasma of raw energy so dense and hot that atoms couldn't exist. Picture a universe filled with free electrons and baratomic nuclei, all swimming in a superheated ocean of radiation. Photons, the particles of light, were constantly being scattered by the swarm of free electrons. They couldn't travel more than a tiny fraction of a millimeter before slamming into another charged particle and ricocheting again. Light had no straight path. The entire cosmos was opaque, glowing from within, but impossible to see through. If you had been able to stand anywhere in that early universe, you would have seen nothing but an endless, brilliant fog, bright, chaotic, blinding. Matter and radiation were locked together in a dance too turbulent to form anything stable. No stars, no galaxies, no structure, only a roiling plasma expanding and cooling. This was a time when the laws of physics we rely on today were still emerging into the conditions that allowed them to operate normally. Gravity tugged gently on the tiny fluctuations in density left by quantum processes during inflation, but the plasma was too hot and energetic for matter to collapse. The entire universe was more uniform than any landscape you've ever imagined, smooth to 1 part in 100,000, with tiny imperfections that would one day grow into everything we see. But something miraculous was about to happen. As the universe expanded, it cooled. Over the span of hundreds of thousands of years, the temperature dropped from trillions of degrees to thousands. At around 3,000 Kelvin roughly, the temperature of a glowing red-hot iron, the chaos finally calmed. At this temperature, electrons could bond with protons and helium nuclei. For the first time in cosmic history, atoms formed. This moment is called recombination, and it changed everything. When electrons attached themselves to nuclei, the fog instantly thinned. Free electrons, the culprits responsible for scattering photons, essentially vanished from the cosmic soup. And with them gone, light was finally free to travel through the universe without interruption, free to carry information across cosmic distances, free to reveal the shape of space itself. The photons released at that moment have been traveling ever since. They spread outward with the expansion of the universe, their wavelengths stretching from visible light into the microwave region. Today we detect them as the cosmic microwave background, a faint, uniform glow that fills every part of the sky. This glow is not an ordinary light source. It's the oldest light in the universe, a fossil of the moment when the cosmos first became transparent. You are literally seeing the universe's first visible moment. When you look at the cosmic microwave background, you're peering through 13.8 billion years of history, catching the earliest image ever obtainable. And it's astonishing what that image reveals. The CMB is not perfectly uniform. It has tiny temperature differences, tiny ripples that correspond to slightly denser or slightly emptier regions of the early universe. Those subtle variations, only millionths of a degree apart, became the seeds of everything. Where the plasma was slightly denser, gravity pulled harder. Atom by atom, those overdense regions grew, collapsing into clouds, then stars, then galaxies, and eventually into the vast cosmic web sprawling across the universe today. Every galaxy, every star, every planet, every atom in your body began as an infinitesimal fluctuation in that primordial plasma. That's why the CMB is often called the baby picture of the universe. It captures the earliest moment where the cosmos could form an image of itself. But the crucial thing is this: the universe before recombination is permanently hidden. No matter how powerful our telescopes become, light cannot reveal anything earlier than that moment because light itself couldn't move freely before it. The early universe is locked behind a wall made not of matter but of opacity. The only way to probe earlier times is through messengers that could move through the plasma, gravity waves, and neutrinos. Future observatories may detect these signals and allow us to glimpse the universe's first seconds, perhaps even the moment of inflation. But for now, our vision begins at recombination. Everything before it lies behind a glowing curtain, invisible to light forever. This moment marks the true boundary of our visible universe, not in distance, but in time. The universe before light is a realm we can never see, but without it, nothing we know would exist. The cosmic microwave background is the oldest light in the universe, a faint whisper from a time when the cosmos was only 380,000 years old. Yet it has become one of the most powerful tools humans have ever used to understand reality. When you look at the map of this ancient radiation, you're not just seeing a glow, you're seeing a snapshot of the universe frozen in its infancy, a baby picture preserved across 13.8 billion years. But what makes this ancient light so extraordinary isn't just its age, it's what it reveals. The CMB isn't perfectly smooth. It's covered in tiny temperature variations, microscopic fluctuations in heat that were imprinted on the universe at the moment it became transparent. These variations appear as splotches, patches, and speckles, each representing slightly denser or slightly emptier regions of the early universe. And these imperfections matter more than you could possibly imagine. They were the seeds of everything. Where the CMB shows a slightly hotter spot, the universe had slightly more matter. Gravity pulled on that matter a little harder, and over billions of years, those tiny overdense regions collapsed into galaxies, clusters, and filaments. Where the CMB shows a colder spot, the universe had slightly less matter, and those regions became the cosmic voids, enormous, empty expanses spanning hundreds of millions of light years. Every galaxy ever formed, including the Milky Way, owes its existence to those microscopic differences in temperature, on a sky we can now measure to a precision of millionths of a degree. But the CMB doesn't just tell us where structure came from. It reveals the shape of the entire universe. When scientists measured the angular size of the temperature fluctuations, roughly 1 degree across, they were able to determine the geometry of space itself. If the universe were positively curved, like the surface of a sphere, the hot and cold spots would appear larger. If the universe were negatively curved, like a saddle, they would appear smaller. But because they appear exactly the size predicted by Euclidean geometry, the universe is flat within a tiny margin of error. This conclusion is staggering. It means that space does not curve noticeably over cosmic distances. It also suggests that the universe extends far beyond what we can observe and may very well be infinite. And the CMB contains even more secrets. The temperature of this ancient glow is now just 2.725 degrees above absolute zero. That's astonishing when you consider it started at around 3,000 degrees Kelvin. As the universe expanded, the wavelengths of the photons stretched, cooling them across billions of years. This cooling is a direct measurement of cosmic expansion. It tells us how fast the universe grew at different stages and gives us the ability to measure the accelerating effect of dark energy. Every pixel in the CMB image carries information about the universe's density, composition, and evolution. From it, we learn that ordinary matter makes up only about 5% of the universe. Dark matter makes up around 27%, and the rest, 68%, is dark energy, a mysterious force driving the accelerating expansion of the cosmos. Without the CMB, we would have no way to measure the cosmic recipe with such precision. But the CMB also teaches us about the earliest fraction of a second after the universe began. The pattern of fluctuations matches predictions from inflation and ultra-rapid expansion that occurred in the first 32 seconds. Inflation stretched tiny quantum fluctuations into macroscopic imprints that later evolved into galaxies. The CMB is the smoking gun for this event. It confirms that our universe was once smaller than a proton and then expanded faster than the speed of light in an instant. Even more remarkably, the CMB tells us that the universe is incredibly uniform. Opposite sides of the sky, separated by more than 90 billion light-years of distance today, have nearly identical temperatures. Without inflation, these regions would never have been in contact, never able to exchange heat or information. Yet they are uniform to 1 part in 100,000. Inflation explains this flawlessly. The entire observable universe emerged from a tiny region that was once connected, allowing it to equalize before expansion tore it apart. So when we look at the CMB, we are looking at evidence not only of the first visible moment, but of the moment before visibility even existed. It is a relic of transparency, a map of density, a test of geometry, a probe of dark energy, and a fossil of inflation, all frozen in a single sphere of ancient light surrounding Earth. And the most poetic part of all, this light will keep stretching, keep cooling, keep fading as the universe expands. One day, trillions of years from now, civilizations far in the future may never detect it at all. The last record of the universe's childhood will slip beyond reach, leaving only the darkness of expansion behind. For now, though, the cosmic microwave background remains our oldest message from the cosmos, a fragile, glowing echo of the moment the universe first opened its eyes. Every photon that reaches your eyes has survived a journey across a universe that is constantly pulling it apart. Light is the fastest thing in existence, but even it cannot escape the relentless stretching of space. This stretching is what we call cosmological redshift, and it slowly drains the energy from every beam of light traveling through the cosmos. Imagine throwing a ball across a field and discovering that the field itself expands while the ball is flying. The ball still moves forward, but the ground beneath it stretches, making the distance longer and the journey harder. Light experiences this same struggle. As the universe expands, its wavelengths stretch, which means its color shifts toward the red end of the spectrum and its energy drops. A photon that began its life as a bright blue spark from a newborn star might arrive at Earth billions of years later as a faint red whisper. Stretch the wavelength even more, and the photon slips into the infrared. Push it farther still, and it becomes microwave radiation. Eventually, after enough expansion, the photon becomes so weak that detecting it is physically impossible. This is the quiet, invisible battle happening to every beam of light as it crosses the universe. And this redshift does more than change a photon's color. It alters the rate at which photons arrive. As space stretches, time stretches with it. Events that take a second in a distant galaxy might appear to take 2 seconds, 5 seconds, or a minute when observed from Earth. We call this time dilation. A supernova explosion that lasts 20 days in its own frame might appear to last 40 days or 60 days depending on how far away it is. Light from each moment spreads out over a longer time, thinning the stream of photons that reaches us. This means that distant galaxies appear dimmer not simply because they are far away, but because their light is being diluted by the stretching of time itself. So the universe dims objects in 3 separate ways at once. First, geometric dimming. Light spreads out as it travels, weakening with distance. Second, energy dimming. Redshift stretches photons, reducing their energy. Third, temporal dimming. Time dilation spreads photon arrival over longer intervals. Multiply these effects, and the light from extremely distant galaxies becomes unimaginably faint, almost ghostly. Our telescopes strain to detect even a handful of photons from galaxies near the edge of visibility. The James Webb Space Telescope, for example, sometimes collects only a few photons per second from the earliest galaxies in the universe, tiny drops of ancient information drifting toward us across a cosmic ocean. But the expansion does not spare any light indefinitely. At some point, photons stretch so far that their wavelengths exceed the background radiation of the universe. Once a galaxy's light becomes fainter than the cosmic microwave background, it becomes indistinguishable from noise. No telescope can separate signal from static. No technology can restore the information. Beyond this limit, the galaxy becomes invisible forever. And because expansion accelerates due to dark energy, more galaxies are being pushed past this boundary every day. Their light redshifts to longer and longer wavelengths until it slips beyond the reach of all physical detection. This is why the edge of the observable universe is not a sharp line, but a gradient of fading visibility. The farthest objects are barely detectable tiny smears of stretched photons that took more than 13 billion years to arrive. Just beyond them are objects so redshifted that their light cannot rise above the cosmic background. Beyond that lies a realm where even the most powerful possible telescope would see nothing but darkness. The universe hides itself gradually, not abruptly. And this fading horizon has consequences for the future. As expansion continues, galaxies that are visible today will drift farther away, their light stretching until it vanishes into undetectable wavelengths. The observable universe will shrink not in size but in content. Fewer galaxies will remain visible. Eventually, only the galaxies tightly bound to our own, those in the local group, will still shine in our skies. All others will have faded beyond detection. To future observers, the universe will appear small, empty, static, and cold. They will not see redshift because distant galaxies will no longer be visible. They will not detect the cosmic microwave background because it will have redshifted into wavelengths too long to measure. They will not know about the Big Bang, inflation, or cosmic expansion. All evidence will have slipped past the reach of observation. We live in a rare moment when the universe is still readable. Light from faraway galaxies still reaches us. The cosmic microwave background still glows. The sky is still full of messages. But those messages are fading. Every second, the universe stretches them a little further. Every second, photons lose a bit more energy. Every second, the cosmos grows dimmer. Redshift is not just a shift in color, it is the slow erasure of the universe itself. Dark energy is the most unsettling discovery in modern cosmology, not because we understand too little about it, but because everything we do know points toward a universe that is accelerating into a future more isolated, more empty, and more unreachable with each passing moment. Imagine gravity pulling inward on the cosmos, trying to slow its expansion, trying to tug galaxies back together, but something stronger resists it. Something pushes outward, stretching space faster and faster. That something is dark energy. We don't know what it is, but we know what it does. It drives the accelerated expansion of the universe. Its presence was first detected in 1998, when astronomers studying distant supernovae discovered that these explosions were dimmer than expected, not because the stars were intrinsically faint, but because the galaxies containing them were farther away than they should have been. The universe wasn't just expanding, it was accelerating. And acceleration changes everything. Before dark energy takes over, gravity plays the dominant role in shaping cosmic structure. Galaxies merge, clusters grow, large-scale filaments form, matter organizes itself. But once dark energy becomes dominant, as it has for the last 5 billion years, the universe enters a new phase. Expansion speeds up. Galaxies drift apart faster than gravity can pull them together. Structures freeze in place. The cosmic web stops growing and begins to unravel. Over time, the distances between galaxies increase so rapidly that light emitted today may never reach other galaxies in the future. Entire regions of the universe become causally disconnected. Dark energy acts like a relentless widening between every unbound part of the cosmos. And here is the key. Dark energy doesn't dilute as the universe expands. Matter spreads out. Radiation weakens. Even dark matter becomes thinner. But dark energy appears to remain constant or nearly constant in density. As space expands, dark energy simply fills the new space. That means the more space there is, the more dark energy there is. And the more dark energy there is, the faster space expands. This creates a feedback loop. Expansion increases dark energy's total effect, and dark energy increases expansion. The result is a universe that accelerates forever, and the consequences are severe. Right now, the universe is about 68% dark energy. In the distant future, that percentage approaches 100%. Everything else, the galaxies, the stars, the planets, becomes an insignificant sprinkling of matter drowned in a sea of expansion. The accelerating universe leads to an event horizon, a boundary beyond which nothing can ever send new information to us. Even visible galaxies are drifting toward this horizon, and eventually, one by one, they will cross it. They will not vanish instantly. Instead, their light will stretch and fade until it becomes undetectable. For a while, we will see only their ancient forms images from billions of years ago, but eventually even those will disappear. The universe is not merely expanding, it is dissolving into isolation. Consider the Milky Way. Today we can see 2 trillion galaxies across the observable universe. But in the far future, tens of billions of years from now, the only visible galaxies will be the ones gravitationally bound to our local group. Everything else will have slipped away behind the horizon. The cosmic night will become deeper. The sky will become emptier. The universe will no longer be a web of galaxies. It will be an island, a single cluster floating in a vast, unreachable sea. And dark energy keeps pushing. In fact, it forces the universe into a state where no future civilization, no matter how advanced, will ever be able to detect the Big Bang. The cosmic microwave background will redshift into wavelengths so long that detection becomes physically impossible. The expansion of space will erase evidence faster than science can preserve it. The universe will look static, eternal, unchanging. Future astronomers will see only a lonely cluster of galaxies surrounded by perpetual darkness. They will have no evidence of expansion, no evidence of the early universe, no way to know the sky was once filled with galaxies. They will live in a cosmic false reality created by dark energy. And the strangest part? This future is not billions of trillions of years away. The process has already begun. The most distant galaxies are already beyond our event horizon. Every day, more cross that line. Dark energy is not a force of destruction. It does not tear matter apart, at least not in its current form. It simply stretches space. But that stretching isolates every part of the universe from every other part. It is the slow fragmentation of reality, a cosmic silence creeping in from the edges. And as dark energy continues its work, the universe becomes a place where the vast majority of existence is forever sealed off, unreachable and unknowable. The universe is not just expanding, it is drifting apart at an accelerating pace, pushed by something we cannot see, cannot touch, and cannot explain. Dark energy doesn't just change the universe, it defines its fate. Picture the universe tens of billions of years from now. The galaxies we see today, 2 trillion of them scattered across an immense cosmic landscape, will have thinned from the sky one by one, fading into invisibility as dark energy stretches space faster than their light can reach us. The vast cosmic web will dissolve into isolation, leaving only the few galaxies gravitationally bound to our own. Imagine looking at the night sky and seeing no giant clusters, no distant spirals, no faint smudges hinting at unimaginable distances. Just darkness, punctured only by the stars of the Milky Way's merged descendants. This future is not science fiction. It is the inevitable consequence of the accelerating universe. The farther out you look today, the younger the universe appears, because light takes time to travel. But in the distant future, the opposite effect will dominate. The observable universe will shrink in content, not in size, but in the number of things we can see. The galaxies that once filled our telescopes will have crossed the cosmic event horizon. Their last photons will arrive, red shifted into oblivion, and then the universe will fall silent. Future astronomers, if any exist, will have no access to the cosmic microwave background, that ancient glow from the birth of the universe. The oldest light we can detect will slip to wavelengths so long that it becomes indistinguishable from the vacuum itself. They will search the sky for hints of the early universe and find none. The signal will be too faint to detect with any conceivable technology because the expansion of space will stretch it beyond the limits imposed by physics. In this lonely future, the Big Bang will not be a discovery. It will be a myth, unprovable and undetectable. The same fate applies to the recession of galaxies. Today we can measure redshift. We can observe galaxies drifting apart. We can detect the fingerprints of dark energy. But trillions of years from now, future scientists will see only a static cosmos, a single gravitationally bound cluster floating in darkness. No expansion, no large-scale motion, no cosmic history, just stillness. The growth of cosmic structures will have stopped long ago, and the large-scale universe will appear eternal even though it was anything but. The irony is tragic. We live in the one brief moment in cosmic history when the universe is still readable, when the sky is still filled with messages, when distant galaxies still whisper their stories across billions of light years, when the cosmic microwave background still glows with the memory of creation. This moment is fragile and temporary. As time goes on, these cosmic libraries will close one after another until the universe becomes a desert of information. Even gravity will eventually lose its power. Galaxies within the local group will merge into a single giant elliptical galaxy, sometimes called Milk Dromeda, a swollen cluster of stars drifting alone in a universe that no longer communicates. With no new galaxies arriving from outside and no external light entering this isolated bubble, the cosmic environment will become a self-contained island. Over trillions of years, star formation will slow. Gas will be consumed. New stars will become rare. Old stars will burn out. The universe will grow dimmer and colder, entering an era sometimes called the degenerate epoch, when stellar corpses, white dwarfs, neutron stars, and black holes dominate the cosmic landscape. But even that isn't the end. Over unimaginable timescales, black holes themselves will evaporate through Hawking radiation, releasing their mass back into the universe as faint, ghostly particles. The fabric of space will become emptier still. Eventually, the universe will be reduced to a thin haze of particles, drifting through an ever-expanding void. And yet, none of this grand cosmic story will be knowable to the civilizations living in that far future. They will look up at the sky and see only a local cluster of stars with no evidence of galaxies beyond. They will have no reason to believe the universe is expanding. They will have no access to the Big Bang. Their cosmology will be incomplete and fundamentally incorrect, not because they lack intelligence, but because physics itself will hide the evidence. This future universe will be a cosmic illusion, a false reality created by dark energy. And the saddest truth is this: we are the only generation of observers who will ever know the full cosmic story. We are alive in the brief window where the universe is still visible, where its past is still accessible, and where its future can be predicted. One day that window will close. The universe will forget its origin. The cosmos will grow silent. And all the evidence we see today, the galaxies, the redshifts, the cosmic microwave background, will be erased by the unstoppable expansion of space. When you imagine the shape of the universe, you might picture something with edges, boundaries, or curves, perhaps a giant sphere, or an endless, flat expanse, or even a loop structure that reconnects with itself. But the real geometry of the cosmos is far stranger and far more revealing than any simple metaphor. To understand the universe's shape, you must understand its curvature, the way space bends, warps, and stretches under the influence of mass, energy, and the laws of general relativity. And the surprising truth is this: measurements of the cosmic microwave background and the large-scale distribution of galaxies show that the universe is extremely close to flat, not curved like a sphere, not saddle-shaped like hyperbolic space, but so close to zero curvature that if it has any curvature at all, it is too small for us to detect across the entire observable universe. A flat universe follows Euclidean geometry, the same geometry you learned in school. Parallel lines stay parallel. Triangles have angles summing to 180 degrees. Light travels in straight lines unless acted on by gravity. But this simplicity is deceptive. A flat universe can be infinitely large, stretching endlessly in all directions, or it can be finite yet unbounded, looping around itself like a video game world where crossing one boundary makes you reappear on the opposite side. Flatness alone does not tell us whether the universe is infinite or merely enormous. But the fact that curvature is so close to zero tells us something profound. If the universe is curved, its curvature radius is far larger than the observable universe, possibly by dozens or hundreds of orders of magnitude. In other words, even if the universe is finite, it is so vast that we can never see its edges. We are like ants walking across a gigantic sphere the size of a galaxy. The surface looks flat to us because it curves so gently that no experiment we can perform would detect the bend. Cosmologists classify the universe into three possible shapes: closed, open, and flat. A closed universe curves inward like the surface of a sphere. Travel far enough in one direction, and you might eventually return to your starting point. A closed universe has a finite volume, but no edges, just like Earth's surface. If the universe were closed, we would expect larger than predicted temperature fluctuations in the cosmic microwave background, because the geometry would distort the scale of ancient acoustic waves. But we don't see that. A closed universe would also eventually stop expanding and collapse in a big crunch, reversing its own creation. But all evidence shows the expansion is accelerating, not slowing. That leaves the open and flat possibilities. An open universe curves outward like a saddle, creating a geometry where parallel lines diverge and triangles have angles summing to less than 180 degrees. But this model doesn't match the observed distribution of galaxies or the CMB either. The only model consistent with our measurements is a universe that is flat to a precision of better than 0.1%. And so the simplest picture yet, also the most mind-bending, is that we live in a universe with no detectable curvature, one that extends unimaginably far, impossibly forever. But flatness brings with it a second mystery. Why is it so perfect? When we measure the ratio of mass and energy in the cosmos, we find it is extraordinarily close to the critical density required for flatness. Even a tiny deviation in the early universe would have amplified over billions of years, creating either a dramatically curved universe or a universe that expanded too fast for galaxies to form. Instead, the balancing act is so perfect, so precise, that it seems almost impossible without some mechanism to force the universe into flatness. That mechanism is inflation. In the first instant after the Big Bang, inflation stretched space by an enormous factor, smoothing out any curvature the universe originally had. Just as blowing up a small balloon makes the surface look flatter and flatter, expanding space exponentially flattens the geometry. Inflation is why distant regions of the universe look so similar. It's why the CMB is uniform. It's why curvature is nearly zero. It's why the universe appears flat even if it is not. And here is the strangest consequence. Even if the universe does wrap around itself, even if it forms a giant loop or a more exotic topology, inflation would have stretched that shape so enormously that any repeating patterns are far beyond our ability to observe. The observable universe may be only a tiny patch on an incomprehensibly larger structure, a fragment of infinity. A piece of geometry so vast that its true shape is forever hidden behind horizons we can never cross. In the end, the geometry of the universe tells us two things. First, we live in a cosmos that follows the familiar rules of flat space, despite being anything but familiar in scale or origin. Second, we inhabit only a vanishingly small portion of an enormously larger whole, a universe whose true shape is stranger and more elusive than anything we can see. The universe did not have to be the way it is. It could have expanded too fast for galaxies to form, leaving behind a cold, structureless void, or it could have expanded too slowly, causing gravity to overwhelm everything and pull the cosmos back into a fiery collapse long before stars or planets existed. But somehow, against all odds, the universe expanded at exactly the right rate, not too fast, not too slow. This perfect balance is known as the critical density, and the fact that the universe has remained so close to this critical value for 13.8 billion years is one of the greatest mysteries in cosmology. We call it the flatness problem. Imagine throwing a ball straight up into the air. If you throw it too hard, it escapes Earth's gravity forever. If you throw it too gently, it rises for a moment and falls back down. But there is one extremely precise speed at which the ball will rise forever, slowing down but never quite stopping. That is the critical threshold between escape and collapse. The universe is like that ball, balanced between expansion and contraction. If the total amount of matter and energy in the early universe had been even slightly greater, gravity would have overwhelmed everything and caused a rapid collapse. If the total amount had been even slightly less, expansion would have run away instantly, stretching the universe so fast that galaxies, stars, and atoms could never form. But the universe did neither. It hovered right at the threshold, expanding slowly enough to allow structure to develop, yet fast enough to avoid gravitational collapse. The unbelievable part is how precise this balance had to be. If the density of the universe 1 second after the Big Bang had been off by just 1 part in 10 or 24, an error smaller than 1 grain of sand in all the beaches on Earth, the universe would be unrecognizable today. That is the degree of fine-tuning required for a flat universe. And yet this unbelievable precision survived billions of years of cosmic evolution. How? Why? Nothing in classical physics explains such perfect tuning, and the mystery deepens when we realize that as the universe expands, any tiny deviation from flatness should grow dramatically over time. Like a pencil standing on its tip, even the slightest imbalance should topple the universe into runaway expansion or rapid collapse. But it didn't. The universe stayed flat to within a fraction of a percent. This is where inflation enters the story. Inflation is the idea that the universe underwent a brief, mind-bending expansion during the first fraction of a second after the Big Bang. In less than 10 or 32 seconds, the universe expanded by a factor so enormous that any curvature it originally had was stretched effectively to zero. It's like taking a small, curved surface and blowing it up until it becomes indistinguishable from flat. Before inflation, space could have been curved in any way imaginable. After inflation, the observable patch was stretched so huge that curvature became undetectable. Inflation acts as a cosmic ironing machine, flattening the wrinkles of space-time and forcing the universe into critical balance. It doesn't just solve the flatness problem, it practically guarantees flatness. And the evidence for inflation is written into the cosmic microwave background. The tiny fluctuations in temperature, those faint patches and speckles sprinkled across the sky, match the pattern predicted by inflation with astonishing precision. The scale, distribution, and amplitude of those fluctuations are exactly what you would expect if quantum ripples were stretched by a massive burst of expansion. Inflation isn't just a clever idea. It is the only explanation we have that matches the data. But inflation leads to an even stranger implication. The critical density of the universe might not be a cosmic coincidence at all. It may be a natural result of physics. Inflation forces the universe toward flatness, smoothing it out just like a powerful expansion flattens the surface of a balloon. The universe wasn't fine-tuned, it was sculpted. Still, inflation itself raises deeper questions. Why did it start? Why did it stop? What triggered it? These remain mysteries. Some theories propose that inflation never fully ends, creating a multiverse in which different regions of space inflate at different rates. Our observable universe might be just one bubble where inflation has stopped. In other bubbles, the density might not be critical. The expansion rate might be different. The laws of physics might vary entirely. If that is true, the fine-tuning we observe could simply be a selection effect. We exist in a bubble where the universe happened to be compatible with life. In bubbles where it wasn't, there could be no observers to question it. Whether or not the multiverse exists, the mystery remains. The universe balances on a razor's edge of density so precise that it defies ordinary explanation. Inflation offers the best answer we have, but even it leaves behind a sense of awe. Why should the universe be so perfectly balanced? Why should the conditions for galaxies, stars, planets, and life be so delicately aligned? The universe didn't just emerge randomly. It emerged balanced so delicately, so improbably, that its fine-tuning remains one of the greatest scientific mysteries of all time. To understand how the universe became the structured, galaxy-filled cosmos we see today, you must travel back to the most unimaginable fraction of a second after the Big Bang, to a moment so brief and so violent that ordinary language completely fails to describe it. This moment is inflation, an event so powerful that it dragged the universe from subatomic size to something large enough to contain all the galaxies that would ever exist. And it did this in less time than it takes light to cross a single proton. If the Big Bang was the universe's birth, inflation was its explosive growth spurt, an expansion not driven by motion, but by the fabric of space itself, doubling in size again and again, faster than the speed of light, in a runaway transformation that reshaped everything. Before inflation, the universe was a chaotic, quantum-dominated realm, smaller than a grain of dust, dominated by energy fluctuations so wild they would tear apart any structure trying to form. Regions of space were disconnected, temperatures fluctuated dramatically, and no large-scale uniformity existed. Yet when we look at the cosmos today, we see something astonishing. The universe is smooth, nearly the same temperature everywhere, with tiny fluctuations that later grew into galaxies. Without inflation, none of this makes sense. How can regions of the universe separated by billions of light years have the same temperature if they were never close enough to exchange heat or information? How can space be so flat, so uniform, when nothing in classical cosmology forces it to be? Inflation answers these questions by proposing that the observable universe began as a tiny, connected region, so small that every part of it could reach every other part. In this minuscule patch, temperatures could equalize, matter could interact, and the rules of physics could settle into place. Then suddenly this patch inflated. Space expanded exponentially, smoothing out curvature and irregularities, stretching quantum fluctuations into vast patterns that would later seed galaxies and cosmic structures. It is as though the universe took a tiny, perfectly mixed droplet of matter and energy and blew it up into a cosmic canvas. Tiny quantum jitters, microscopic wiggles in the fabric of space-time, were stretched to macroscopic scales. Places that were slightly denser became the gravitational wells where galaxies formed. Places that were slightly emptier became the voids. Inflation is the artist behind the cosmic web, painting the universe with patterns born from quantum foreshocks. And although inflation happened faster than light, it did not violate relativity. Nothing moved through space faster than light. Instead, space itself expanded faster than light. Relativity does not restrict the expansion of space-only motion within space. Inflation exploited this loophole, expanding the universe trillions of times over in an instant. When inflation ended, its enormous stored energy transformed into a hot, dense plasma, the beginning of the Big Bang as we usually imagine it. In fact, the familiar expanding fireball of the early universe is not the moment of creation. It is the aftermath of inflation. The heat and particles of the Big Bang were created when inflation's potential energy decayed into matter and radiation. This is the moment when the universe became hot, filled with particles, and ready to evolve into stars and galaxies. Without inflation, the universe would be curved, chaotic, and broken into disconnected regions. Galaxies would not exist. The cosmic microwave background would be patchy and uneven. The large-scale structure of the universe would have no reason to match the patterns we observe. Inflation is the only theory that explains the uniformity of the cosmic microwave background, the flatness of space, and the distribution of galaxies all at once. But the story grows stranger. The mathematics of inflation suggest it might not be a one-time event. Inflation may happen again and again in different regions of space, producing countless bubble universes, each with its own physical laws, constants, and dimensions. In some bubbles, inflation ends, creating universes like ours. In others, it continues eternally, stretching space forever. This idea is known as eternal inflation, and it implies that our observable universe may be just one pocket in an infinitely larger multiverse, a single drop in a cosmic ocean with no shore. Each drop might contain different forms of matter, different strengths of gravity, even different numbers of dimensions. The multiverse is not proven, but it is a natural consequence of the same equations that give us inflation. If inflation happened once, it may happen endlessly. And the strangest part of all is this. Everything you see in the universe, every star, every galaxy, every atom originated from quantum fluctuations stretched by inflation. All of cosmic structure, all of cosmic beauty, began as ripples in the fabric of space-time, smaller than the smallest known particle. Inflation took these tiny ripples and expanded them into the blueprint of the universe. In a real sense, the universe was written in quantum handwriting, etched into its earliest moment and magnified to cosmic scale. When you stand on Earth and look out into the night sky, every star, every galaxy, every cluster you can possibly see is part of the observable universe, not the whole universe. Beyond that sphere of visibility lies a realm so vast and so unreachable that it makes everything we can observe look small, like a tiny island in a limitless ocean. And the strangest part is this: the universe beyond our horizon might look nothing like the universe we know. The regions outside our observable bubble are not merely farther away, they are separated from us by the accelerating expansion of space itself. Their light has not had enough time to reach us, and due to dark energy, it will never reach us. But just because we cannot see them does not mean they are empty. Cosmology suggests that the unobservable universe is at least hundreds, thousands, or even infinite times larger than what we can access. The observable universe contains 2 trillion galaxies. The unobservable universe may contain a number of galaxies so large it defeats language. Even calling it infinite barely captures the scale, because infinity in mathematics is not just one size. There are infinities larger than other infinities, and the universe may occupy levels of immensity that we cannot even describe. But what lies in those unreachable regions? The simplest possibility, and the one most cosmologists expect, is that the universe continues more or less the same way it does here. More galaxies, more stars, more clusters and voids stretching endlessly. More filaments of dark matter weaving a cosmic web that extends forever. In this picture, the unobservable universe is just more of the same cosmic tapestry, repeating the same kinds of structures with no special variations. But the universe may not be so predictable. Inflation, the rapid expansion that shaped the early cosmos, may have produced vast regions that are slightly different from ours, places where quantum fluctuations led to density differences, temperature variations, or even different cosmic structures. These would still obey the same physical laws, but the cosmic scenery might be dramatically different. Clusters might be more massive, galaxies might be more tightly packed, or the ratio of dark matter to ordinary matter might vary subtly. These changes would ripple across billions of light years, producing cosmic neighborhoods unlike anything near us. But some theories go even further, suggesting that inflation can produce regions of space with entirely different physical laws. These ideas, often referred to as the multiverse, propose that inflation does not end everywhere at once. Instead, in some regions, inflation stops and a universe like ours forms. In others, inflation continues forever, preventing structure from forming. And in still others, inflation ends in a way that causes the laws of physics to take on different values, different particle masses, different forces, even different numbers of dimensions. In this picture, the cosmos beyond our horizon is not simply more of the same, it is different in ways we can barely imagine. A region not far beyond our observable sphere might have galaxies similar to ours. A little farther could be regions where stars form differently or where galaxies cluster into more complex shapes. And far beyond that might be bubbles of space with entirely different physics. These regions are not part of our universe in any practical sense. Their light will never reach us. Their galaxies will never interact with ours. Their physics may be incompatible with our own, yet they exist within the same overarching framework of space-time. The observable universe is just one cosmic patch among an enormous quilt of possibilities. And here is the most mind-bending part. Because the universe is expanding faster than light over large distances, the boundaries between these regions grow every second. More of the cosmos slips out of view, and the portions that remain eternally unreachable expand beyond imagination. The universe outside our horizon is not just big, it is growing faster than our ability to understand it. Every second, trillions of cubic light-years of space become permanently hidden. The unobservable universe is not static. It is a frontier that recedes forever. If you could teleport to a galaxy near the edge of visibility, your observable universe would shift. You would see galaxies that no observer on Earth can ever see. Move again, and you would unlock a new cosmic sphere, filled with structures invisible from your previous location. In this sense, the universe is not a single observable entity, but a collection of overlapping horizons, each centered on a different observer. Each horizon reveals only a fragment of reality, like windows carved out by the speed of light in the age of the cosmos. What lies beyond those windows is the true universe, vast, diverse, and permanently hidden. We will never see it, never reach it, never interact with it, but it surrounds us completely, pressing in from all directions like an infinite, unreachable ocean. Imagine living inside a universe so vast that even if you traveled in a straight line forever, you might never find an edge. Not because the universe is infinite, but because space might loop back on itself. This is the strange and beautiful world of cosmic topology, the branch of cosmology that explores the universe's possible shapes on the largest scales. We tend to imagine space as flat and infinite, stretching endlessly in all directions. But the universe could be finite without having any boundaries at all, just like the surface of a sphere. You can walk endlessly around Earth without ever finding a wall or an edge, and yet Earth's surface is finite. Scale that idea up by 3 dimensions, and you get a universe that loops around itself in ways that defy intuition. One of the simplest possibilities is a 3-dimensional torus, the higher dimensional version of a donut. In such a universe, traveling far enough in one direction might eventually bring you back to your starting point. Space would wrap around itself, creating a cosmos with no edges and no center, yet with a finite volume. It would feel infinite from the inside, just as Earth's surface feels infinite to an ant. But the torus is only one option. Space could fold, twist, or connect in exotic ways allowed by higher dimensional geometry. Some models propose universes where opposite faces of a cosmic cube are glued together, so that exiting through one side brings you back through the opposite side. Others suggest that space might be connected like the hallways of a video game level that loops seamlessly. There are even topologies in which space is connected through wormhole-like shortcuts called multiply connected manifolds, where different regions of the universe are actually the same region seen again and again from different directions. If this sounds fantastical, remember that topology is not science fiction. It is a branch of mathematics that general relativity allows. Einstein's equations describe how space bends and curves, but they do not dictate its global shape. Topology is geometry's wild sibling, free to create structures that satisfy the laws of physics while defying common sense. But if the universe loops around itself, shouldn't we see repeating patterns in the sky? In theory, yes. If space were small enough, we could look far enough in one direction and see our own galaxy from the back. Light would wrap around the cosmos, showing multiple images of the same structures at different ages. This would create symmetrical features in the cosmic microwave background patterns and alignments that betray a repeating universe. Cosmologists have searched for these signatures. They've looked for matching circles in the CMB, identical temperature patterns that would indicate we are seeing the same region of space from different angles. They've looked for duplicated galaxies, for repeating alignments, for mirrored structures stretched across the sky. So far, the results suggest that if the universe is multiply connected, its topology is too large for us to detect. The most sensitive searches show no repeating patterns within the observable universe. This means that if the universe loops, the scale of that loop must be larger than 46 billion light-years in all directions, larger than the entire region we can see. In other words, the universe may be finite, but too big for us to notice its finiteness. But topology doesn't stop there. A universe can be flat and infinite, flat and finite, curved and infinite, or curved and finite. The geometry we observe, nearly perfect flatness, does not reveal the topology. Space could still be finite even if it behaves locally like flat Euclidean geometry. Topology hides on the largest scales, beyond horizons we can never cross. Inflation complicates this even further. During the universe's first fraction of a second, inflation stretched space so much that any pre-existing topology was blown up far beyond our observable region. If space had loops, twists, or connections before inflation, they are now too large for us to detect. The observable universe might be only a tiny patch of a far larger manifold whose full shape is forever hidden. Some theories propose that the universe could be shaped like a higher dimensional sphere, a projective plane, or other exotic manifolds with properties unlike anything in our everyday experience. These shapes would create subtle patterns, alignments, anomalies, or distortions in the cosmic microwave background that might hint at a deeper structure. Some anomalies do exist. The so-called axis of evil, a strange alignment in the CMB's largest scale fluctuations, has led some to speculate about unusual topology, but no definitive evidence has emerged. The truth is that cosmic topology sits at the edge of what science can measure. We may never know the true shape of the universe, not because the question is meaningless, but because the universe may be too large, too stretched, or too disconnected for its shape to reveal itself. The cosmos could be infinite. It could be finite but boundless. It could loop around itself in dimensions we cannot visualize. We might live inside a cosmic donut, a hypersphere, a twisted manifold, or a patch of an unimaginably larger structure. And the most humbling possibility is this: the true shape of the universe may be something no human mind has ever conceived. If the universe is infinite, and every measurement we have suggests it might be, then the most unsettling consequence is not its size, but what infinity requires. In an infinite cosmos governed by the laws of physics we know, with particles that can arrange themselves in only a finite number of ways, repetition becomes not just possible, but inevitable. Somewhere out there, unimaginably far away, there could be another Earth, another sun, another galaxy shaped like the Milky Way, another version of you, built from atoms arranged in the exact same pattern, living an identical life up to this moment. And farther still, another version of you living a slightly different life. And farther than that, versions whose lives diverged in ways small at first, then enormous. This is not fantasy, it is mathematics. If the universe is infinite, and the number of possible quantum states within a finite region is limited, then the combinations must eventually repeat. The universe becomes a cosmic lottery with infinite tickets, but only finitely many outcomes. Once the number of regions exceeds the number of possible configurations, duplicates appear. But the strangeness does not stop with exact copies. Even if exact repetition is unimaginably distant, the broader concept is far more immediate. In an infinite universe, every possible arrangement of matter that obeys the laws of physics must occur somewhere. There will be regions with galaxies far brighter than anything near us, regions with galaxies too faint to form stars, regions where planets orbit double suns or drift alone in the dark. Somewhere, there are cosmic neighborhoods where the ratio of dark matter to ordinary matter produce structures unlike anything we have ever seen. Somewhere, galaxies form earlier or later, or never at all. Infinity guarantees variation, but it also guarantees repetition. Think of the universe divided into spheres, the size of the observable universe. Each sphere contains a finite number of possible configurations, possible galaxies, possible planets, possible life forms. If the universe contains an infinite number of such spheres, then some must repeat. The distance to the nearest identical sphere would be so vast that no language can express it. Numbers like 10 or 10 100 Miles are tossed around, but the distance is not what matters. What matters is that infinity allows even the impossible to become inevitable. And what about versions of you? This idea may feel philosophical, but it comes straight from physics. The arrangement of atoms in your body is one possible configuration among an unimaginable number of others. But that number, while staggeringly large, is still finite within a finite volume. In an infinite universe, there are infinite opportunities to generate that configuration again. Somewhere particles in a distant region have assembled into a person whose memories, thoughts, and actions are indistinguishable from yours. Somewhere else is a version of you who made one different choice, then thousands of different choices, then an entirely different life. You might imagine these copies as science fiction parallel universes, but the truth is far more grounded. They would be part of the same physical universe, just far beyond any possibility of communication. The accelerating expansion ensures that no signal could ever reach them. They are as unreachable as alternate realities, even though they exist in the same cosmic fabric, and yet infinity expands the possibilities even further. If inflation produced a multiverse, countless bubble universes with different physical constants, then repetition occurs not only across space but across universes. In some bubbles, gravity might be stronger. In others, stars might never form. In some, chemistry might be impossible. And in a tiny fraction, an unimaginably tiny fraction, conditions might permit life, consciousness, and beings capable of wondering whether they are unique. In that picture, the existence of a universe like ours becomes a statistical necessity, not a cosmic miracle. But even without invoking a multiverse, an infinite universe alone is enough to ensure that every allowed configuration appears somewhere. The true weirdness is not that there may be copies of you. The weirdness is that in an infinite cosmos, not having copies would be mathematically impossible, and the philosophical implications cut deep. If countless versions of you exist, what makes you you? Are you defined by your specific atoms, your memories, your choices? Or are you simply one instance of a pattern that emerges whenever the right conditions align? These questions do not have easy answers, but they reveal something profound about the universe. The cosmos is not obligated to be comfortable or simple or centered on our intuition. It is obligated only to follow the rules encoded in its physics. And if those rules permit infinite size with finite possibilities, then copies, variations, and repetitions are not bizarre. They are required. Somewhere out there, the universe may be repeating itself endlessly, and everything you are experiencing right now may be just one thread in an infinite tapestry of cosmic duplicates. When you try to imagine the edge of the universe, your mind reaches for something familiar, a wall, a border, a frontier that marks where everything ends. But the true edge of the universe is not a place you can travel to or point at. It is a limit woven into the fabric of space-time itself, a boundary made of time, expansion, and the unbreakable laws of physics. The strangest truth in cosmology is this: the universe may be infinite, but the part we can experience is brutally finite. Our observable universe is a sphere centered on us, not because we are special, but because light travels at a fixed speed and the universe has existed for a finite time. The edge we see is not where the universe ends. It is where our ability to receive information ends. Beyond that lies more universe, likely far more than we can comprehend, but it is forever hidden behind a horizon defined not by distance, but by time. And this boundary is not static. It moves, evolves, and slowly erases our view of the cosmos. Each second, ancient light arrives from regions that were once too distant for their photons to reach us. This expands our visible universe. But at the same time, dark energy accelerates the expansion of space, pulling galaxies away so quickly that new light emitted from them today will never arrive. The universe shows more of its past while hiding more of its future. The cosmic horizon is a one-way surface. Information from beyond cannot cross into our region, yet our region continually inflates, swallowing more space that will never become visible. Even the galaxies we can detect now are fading, their light stretching into longer wavelengths as expansion siphons energy from their photons. Over immense timescales, the most distant galaxies will disappear from view entirely. First they will dim, then redshift into infrared, then microwave, then radio, and finally into wavelengths too long for any conceivable detector to distinguish from the background of empty space. What remains will not resemble the universe we see today, but perhaps the most haunting aspect of the universe's edge is this. It is not a fixed boundary in space, but a moving horizon defined by the limits of causality. Every observer on Earth, in Andromeda, or on a planet orbiting a star trillions of light years away, sees themselves at the center of their own observable sphere. Each has a different cosmic horizon. Each sees a different version of the universe. The cosmos is not a single shared view, but a patchwork of overlapping perspectives, each bounded by its own horizon. Move to another galaxy and your horizon shifts. Travel far enough, if that were possible, and you would see galaxies we can never see from Earth. Every observer carries a different fragment of reality. The full universe is all those fragments combined, yet no one observer can ever experience the whole. This is the deepest meaning of the cosmic horizon. The universe is too large to be known in its entirety, even in principle, not because our technology is limited, but because the laws of physics themselves draw the boundary. And beyond that boundary, the universe does not stop. Whether it is merely unimaginably vast or truly infinite, it continues far past the limits of observation, filled with galaxies, structures, and phenomena we will never detect. Some of those regions are simply too distant. Others are forever beyond the cosmic event horizon, because expansion carries them away faster than light can close the gap. And if the multiverse exists, if inflation created endless bubble universes, then beyond our horizon might lie realms with different physics, different dimensions, perhaps even different concepts of space and time. We may live in a single cosmic bubble adrift in a sea without shores, but even if we ignore the multiverse and consider only our own universe, the conclusion is the same. The true edge is not a place, but a limit of knowledge. The universe hides most of itself not behind walls, but behind the rules that give rise to space and time. We exist in a cosmic island of visibility, surrounded by an ocean of unreachable reality. And as the universe expands, that island shrinks in content, even as it grows in size. The edge moves, the horizon recedes. The cosmos becomes less knowable with every passing era. Yet within this fleeting moment, right now, we can still see the universe in all its sprawling splendor. Galaxies, cosmic webs, ancient light, the afterglow of creation. We live in the only era when the universe reveals its full story. The horizon will close eventually. The universe will fade. But today the cosmos is still open, still visible, still speaking, and we are here to listen.